Hello, pre-calculus students and seekers of general truths. We continue our practice of the principle of mathematical induction with a very helpful formula here, the proof for the sum of squares. And let's understand a little bit further what this statement is saying. This is really saying 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared plus, and you can keep on going as far as you want, up to some value of n squared, and that's going to equal to n times n plus 1 times 2n plus 1, all of this over 6. Okay? And one thing I want to point out again is that when we are talking about these values of n, it's not that n is equal to 1, 4, 9, or 16. N is just a counter. N is always increasing by 1. 1, 2, 3, 4, 5. In other words, n is like the input that we're putting into a formula. Okay? And we want to show that the sum of all these individual squares can be evaluated more effectively using this neat little formula that we have here. Okay? So, and to do that, we do what we've done before. Let's start with the base step. This is when n equals 1. So we see, well, is this even true for the narrowest cases? Okay. Well, on the left-hand side, if n is equal to 1, all we have is just 1 squared, so that's equal to 1. On the right-hand side, we have 1 times 1 plus 1 multiplied by 2 times 1 plus 1. Okay. All of this over 6, which is equal to 2 times 3 over 6, which is equal to 1. Okay, so once again, the left-hand side and the right-hand side are equal. So we know that this works at least in the base case. Okay. Now, can we show that this is true for let's look at the inductive step. We are going to assume that the formula is true for n equals k, and we want to show that it's true for n equals k plus 1. In other words, we want to show that 1 squared plus 2 squared plus 3 squared plus 4 squared, so on, 5 squared, 6 squared, all the way to n equals k squared, and then one step further, all the way to n equals k plus 1. So we want to show true for n equals k plus 1. Okay. So we want to show that the formula we have here is true even when n is equal to k plus 1. So the right-hand side of this would be kind of complicated. K plus 1 times k plus 1 plus 1, so that's k plus 2, times 2 times k plus 1 plus 1 again. Okay, so we're replacing all of our n's with k plus 1. Okay. All of this over 6. Okay. And again, to show this, we rely heavily, and it's really one of the nice things about induction is there's like only 1 or 2 things you can do. We're going to use the inductive step here, the inductive assumption, because we get to assume that the formula is true for n equals k. So all of this right here is going to be equal to what we set our formula to be. K times k plus 1 times 2k plus 1, all of this over 6. And then we're adding on another quantity, k plus 1 squared. And as usual, we want to be able to combine these statements together, so we're going to make them the same denominator. And then we will slowly work through the details from here. All right, so working through all of the details, what we have is the statement that we can combine together. So k times k plus 1, 2k plus 1, plus 6 times k plus 1 squared. All of this over 6. And we're trying to show that this expression will be equal to the right-hand side. Okay. So let's keep going with this. Maybe the simplest, perhaps the cleanest way to approach this is just to factor out a k plus 1 out of both of the terms here. So if we factor out a k plus 1, what we end up with here is k times 2k plus 1 plus 6k plus 1. Because we used to have this square here, so we factor out one of the k plus 1 terms, and now we're just ending up with 6 times k plus 1. And then if you notice here, what we're trying to show in our formula is that we're going to have a k plus 1, and we're somehow going to have a k plus 2, and somehow we're going to have this term here on the inside. And we're getting something relatively close to it, but it's still quite messy. So it might be the best thing to do here just to distribute or to FOIL or whatever terminology you want to use here, all the stuff that's inside of the square brackets. So let's do this workout. This is going to be 2k squared plus k plus 6k plus 6. All of this over 6. Okay. Everything that's inside of the square bracket here is going to be k plus 1. And then the stuff in the square bracket is 2k squared plus 7k plus 6. And all of this being divided by 6. So this is our left-hand side, right? This is the left-hand side. And you see, it's like we could keep on trying to factor it, but it may also be helpful at this point for us to just work through the right-hand side a little bit here. So if we take the right-hand side, and I'm sorry that this is a little bit messier than I wanted it to be. Okay, but like if we use the right-hand side here. So let's just work on the right-hand side a little bit. Use a darker pen. Okay, so we use the right-hand side. We have a k plus 1 already. We have a k plus 2. And in here, if we multiply all that out, we get 2k plus 2 plus 1. All of this over 6, which is equal to k plus 1 times k plus 2. This is 2k plus 3. Okay. All of this over 6. And yeah, let's go one step further. And if everything works out, we should be able to distribute. If we distribute k times 2k, we get 2k squared. Then the middle terms is going to give us 6k. I'm sorry, it's going to give us 3k plus 4k. So that's 7k. And then the last term is 2 times 3. So that's going to give us 6. And all of this is being divided by 6. So now we've gotten to a good place where the right-hand side of the equation of the formula matches perfectly with the left-hand side of the formula. And thus the proof is complete. Okay? So there's a lot of complicated algebra, or rather messy. I wouldn't say it's too complicated, but it is messy algebra that goes into this. Don't lose sight of the fact, though, that what we're trying to do is we are making an assumption about a generic value, k, and we are showing that using that assumption, our formula or our claim must also be true for k plus 1. Therefore, it's true for all values of n. All right, so as always, thank you for working hard. Thank you for watching this video honestly. And keep working at this. This will take some practice, but it's certainly within your reach. Ask for questions when you need it, and have a wonderful day.